Hi everyone, here's Fabien and my name is Tony, and we are happy to present a work which consisted in measuring the coherent backscattering peak of translucent materials to you. And so first, let's talk about this in nature, because this phenomenon can occur in nature. And right here, there is an example of backscattered light, which was formed in the fog, because this phenomenon occurs when some light comes on a diffusing medium. And as you can see, there is a halo, a luminous halo in the middle, and the shadow of the photographer in the middle of this halo, because he was just in front before the source, which is the sun. And this is linked to the fact that when the lights comes on diffusing medium, it encounters several asperities and diffusing elements. And if the light is diffused in all the direction, but two waves can follow the same path, and then they are the same phase, and they will have the possibility to interfere constructively, and then it will lead to the presence of this peak of intensity. So we decided to measure it for several diffusing materials, and for this we decided to set up a device to test it, to take pictures and then have intensity curves, and then it will give us the possibility to measure the mean free path within the one parameter of the materials.
So our first difficulty that arises is that the light is taking the same path in both in return. So of course you can't put yourself between the light source and whatever you're illuminating, or you'll have a problem. So we can solve this with a glass plate. The light, will come from the source, traverse the glass plate, be retrodiffused, and some of it will be reflected, so we can get it there in the symmetrical position. So this setup provides some images, and when we move it around, we can see the spot that is present in the symmetrical position relative to the lamp. But these images aren't really good, so we need some better setup.
Oh yes, we decided to use a collimated setup device, where by using a collimator lens and puts the source in its focus, and then imaging it with a camera. And it allows to have to collect more light and less stray light.
Then we have some pictures that we have to treat to extract data from it. So we have to take several pictures in different configuration to isolate the peak from the background. So these are the kind of picture we have. You can see a little stain here. And we move the setup around, and you can see the peak traveling. These are better pictures, but still you can see some background. There's less light in the corners. So we have to first take pictures of the background to know how much it darkens on stuff like that. And then we have that.
And it showed that the importance of the size of the lamp, because in fact the peak is collimated with the lens. Convoluted with the lamp. Thank you. And then the fact is that the peak is bigger than what it should be, and then we can find a compromise by using a pinhole to reduce the size of the lamp. And ideally, the lamp should be punctual, but there is not enough light, and it is impossible to see anything. So here are the first results that we get with two with two samples, which are paper and a spectralon, which is a kind of paint which is used to calibrate optical devices. And so they are on the curves. You can notice that there are three curves which corresponds to the three channels of the camera. And then we can notice the presence of the peak. And on the x-axis, there is the radial coordinates, the distance from the center of the peak. And for example, for the spectralon, the radius of the peak is approximately 0.15 degrees, which corresponds to approximately 0.2 millimeters for the mean free path. And but data are quite noisy and difficult to explain. Here, we tried with more diffusing materials, so two white plexiglasses. And here you can see the fact that the two plexiglass, the diffusivity of the two plexiglass is different because the halo of light is not the same. And but these materials were too diffusing, and we can't notice the presence of the peak on the curves. And then we tried to do it with even more diffusing materials, which are soap and stained glass by Pierre Soulages. But as you can see, the peaks were too thin to be detected, and then the data were not, we can't analyze them.
Yeah, so we couldn't observe any peak for the more diffusing materials. After reviewing the equation, it's because the amplitude of the peak is always the same. So the thinner the peak is, the less energy it has in total. And once it has been convoluted by the lamp, it's spread around and we can't see it as easily. And for really diffusing material, light can travel far, and this makes a really thin peak, and it makes it out of the sensibility of our setup. So in conclusion, we could observe the phenomenon and even see it with the naked eye, but for the harder materials, our setup has its limits, and we don't quite know how far we could push it with white light, that is simpler to use than laser light, but an amelioration could be to use laser light. It's more complicated, but it works in the studies we read. That's about it, I think.